Welcome to my talk on the analysis of annotated networks via the sparse beta model. I am Stefan Stein, and I'm doing my PhD in statistics at the University of Warwick under the supervision of Chen Lei Lang. When I speak of annotated networks, I mean that we observe a simple undirected graph G with some additional node or edge information. For this talk, I will identify a graph with its adjacency matrix, which I denote by capital A. When we talk about random networks, we distinguish between two regimes. A network can be dense, and is called dense if the expected number of observed edges scales as n squared. On the other hand, it is called sparse if that number scales as n to the kappa with the kappa strictly less than 2. A thing to point out here is that if we restrict the link probabilities in our network away from 0, then we will automatically be put in the dense network regime. However, real networks are almost exclusively sparse. Also, they exhibit something called degree heterogeneity, which means that the degree distribution has heavy tails. So we have some nodes with a very, very high degree. And finally, real networks also very frequently exhibit homophily, which means that similar nodes are more likely to connect to one another. The model I'm going to present to you today is designed to specifically capture these three properties of real networks. That model is the sparse beta model with covariates. It is an extension of the sparse beta model, which was introduced by Chen et al. In a 2019 paper. In this model, we assume that for each pair of nodes I and j, we observe some bounded centered p-dimensional covariate vector Zij, where p is assumed to be fixed. Then given this covariate vector, the probability of observing an edge between I and j is given by this formula, where we have assigned a popularity parameter to each node. If this beta I is large, then node I will have many connections. If it is small, it will have few connections. So this part of the formula captures the degree heterogeneity. We then have a global sparsity parameter mu, which is allowed to go to -infinity as n goes to infinity. This captures the sparsity of the network. And finally, we have a weighted sum of our covariates. This captures the homophily. For identifiability, we assume that the minimum beta is equal to 0. If we leave away that condition and the mu and the covariates, then this becomes the beta model, which is a flexible network model, but only allows consistent parameter estimation for dense networks. When we add the mu, we are able to model sparse networks. For nodes that both have 0 beta, this model behaves like an Erdős-Rényi model with link probability going to 0. And then we have a few very popular nodes that will have a very high degree. So we can say that the sparse beta model interpolates the Erdős-Rényi model and the beta model. It's also to note that in this model we have a double sparsity. For one, we are modeling sparse networks. On the other hand, we also have a sparsity in our parameter by assuming that the minimum beta is equal to 0. Here I have a few network realization to give you a conceptual idea of what this might look like. On the left, we have the Erdős-Rényi model, for which a sparse theory exists, but in which each node has more or less the same degree as indicated by the size of these little dots. In the middle, we have a realization of the beta model, which has quite a big variability in the degree distribution, but which is rather dense. And then finally, on the right-hand side, we have a realization of the sparse beta model, which has still a big variability in the degree distribution, but results in sparse networks. And the orange-colored nodes here are those nodes with a beta larger than 0. Let's fix some notation. We use theta to denote a generic parameter, and pij of theta to denote the associated probabilities. Theta 0 is the truth, and its sparsity is denoted by S star. We make the following sparsity constraint. We assume that there is a sequence rho n0 going to 0 that bounds our link probabilities almost surely. And then we define our parameter space, big theta, for a given rho n as exactly that space of the parameter vectors, theta, for which the associated probabilities are bounded by that rho n. For this talk, we assume that the rho n in our parameter space is smaller than the rho n0. That means that the truth is actually contained in this parameter space. We also have a theory for the case when this is not the case, but then we have a deterministic bias in our error bounds, and the theory is not as nice, so we focus on this nice theory here. Having said all that, for the actual parameter estimation, we use a penalized likelihood approach. We take the negative log likelihood, and then we put an L1 penalty on the sparse component of our parameter vector, on the beta. In the original sparse beta model, the authors were able to use an L0 penalty here, which, as we know, is not convex, so normally it's not computationally tractable, but their solution space to this problem has a special form, which allows them to use the L0 penalty. But once we add the covariates into the model, this form breaks down, and we need to use the L1 penalty, which essentially is a convex proxy for the L0 penalty. This looks a lot like penalized logistic regression, although there are some significant differences. For one, we are allowing our link probabilities to go to zero. And secondly, our parameter components have different effective sample sizes. If you think about it, the mu and the gamma play a role in the link formation of all possible n-choose-2 edges in our networks, whereas each component beta I only plays a role in the up to n-1 edges that vertex I can form. That means the effective sample size of each beta I is only n-1, whereas it is n-choose-2 for mu and gamma. The result of this is that the standard compatibility condition, which is crucial in standard lasso theory to prove consistency, does not hold in our model. To fix this, we need to adjust for different sample sizes. I have the exact conditions on the next slide, and I invite you to pause the video for a moment to read through it. But essentially, what these conditions say is that we need to put the assumptions on our sparsity and choose our penalty according to the sample size associated with beta. When we impose all of these conditions, we have the following main result, which is a consistency result for the L1 error that we are committing. If we look on the right-hand side here, we see that our error bound that we get consists of the sparsity, and then here the square root of the log of the number of columns divided by the number of rows in our model. And then we have an additional factor 1 over rho n0, which goes to infinity. This additional factor is precisely the price we have to pay for allowing our link probabilities to go to 0. Because to put this into context, in classic lasso theory, we would expect to get sparsity times square root of log number of columns divided by number of rows. So up to this extra factor, we already see that mu and gamma have exactly the rate of convergence of a lasso type estimator of sample size n-choose-2. And if we solve for beta here, we see that again, up to this extra factor, we get exactly the rate of convergence of a lasso type estimator of sample size n-1. So that is quite remarkable, and I think quite beautiful that we are able to recover the lasso rates of convergence here despite them having different sample sizes. Our second main result concerns the inference for gamma. Imagine you are an applied statistician, then one of the most pressing questions you might have is which role do the covariates play in the network formation? So you want some inference result on the gamma. If we assume some additional assumptions, so this one is only a stricter form of assumption 1 that we had before, and the other one was a rather harmless assumption, then we get this theorem, which says that under the appropriate scaling, each component of my estimator for gamma is asymptotically standard normal. And this matrix sigma hat is just the Hessian of the negative log likelihood with respect to gamma evaluated at theta hat. So if you're familiar with Lasso theory, you might say, hold on, how can this be? Lasso is biased, we know that. Now I claim that these gamma estimates are not biased. And the reason why I do not need a debiasing procedure here is that the bias, which is incurred from the beta, because the beta is penalized, so the beta estimates are going to be biased. This bias is going to vanish fast enough because, essentially, because the part of the design matrix associated with beta is so sparse such that its matrix norm is going to be small in comparison to the effective sample size of gamma. And that's why we do not need to debias at this point. These results are also corroborated by our simulations. Feel free to pause the video here again to read through our simulation setup. Essentially, we have increasing sparsity, different network sizes, parameter values that are increasing with n. N is the number of nodes in our network, and mu going to minus infinity, and covariate dimension of 2. And if we look at the results, we see that the edge density is indeed quite small, which is what we want. And when we construct 95% confidence intervals, then the empirical coverage is actually quite close to that 95% nominal value. And the median length of our confidence intervals is decreasing as desired. If we look at the absolute errors that we commit, we see that they all decrease with increasing sample size, which is what we want. And this brings me to the end of my talk. Thank you very much for listening. If you have any questions, feel free to shoot me an email. And I look forward to our Q&A session. Thank you very much.